Imagine hiring like the smartest human being on earth to run your company strategy. I mean, they've read every book, they understand quantum physics, they speak 50 languages.
But there is a massive catch.
Right, a huge catch. This absolute genius has severe, permanent short-term memory loss.
Yeah,
They think it's still 2023, they physically cannot read your internal emails, and they have zero idea what your team discussed in the boardroom 10 minutes ago.
which is incredibly frustrating.
Exactly. And that frustrating scenario is exactly what happens when you try to deploy a large language model today without fixing its memory. Welcome to today's deep dive.
What's fascinating here is that this is the defining architectural bottleneck of our time. I mean, we've engineered these models to exhibit just startling reasoning capabilities, but
But they're completely isolated.
yes, completely isolated from the real-time operational reality of the businesses that are actually trying to use them.
And that is the core mission of our deep dive today. We're looking at this phenomenal breakdown from IBM Technology that explores the battleground of how we actually fix this amnesia.
Because right now, an LLM is it's essentially frozen in time.
Right.
The second the engineers finish training it, like the moment they stop feeding it data and lock its neural weights, it stops learning, period.
It's done. I mean, it might know the entire history of the Roman Empire up to its training cutoff, but it doesn't know your company's Q3 revenue.
No.
It doesn't know your proprietary code base, and it definitely doesn't know the updated HR policy you published this morning.
And the general public often misses this distinction.
Yeah.
You know, they interact with an AI and they just assume it's querying the live universe.
Yeah, like it's just Googling things in the background.
Exactly. But the reality is the base model is a static file. It is this massive, complex mathematical web of probabilities, but it's entirely static.
Right.
So if you want that brilliant but amnesiac system to be useful for your specific daily tasks, you have to find a way to inject your reality into its brain at the exact moment you ask it a question.
Context injection, that's the technical term, right?
That's the one.
How do we take your private, messy, massive pile of data and inject it into the model's active memory so it can actually answer your question?
Right.
And the IBM source details this massive clash between two fundamentally different ways to solve this. We are basically looking at an architectural war
A huge one.
between RA, which is this intricate, highly engineered pipeline, and long context, which is basically, I don't know, taking a sledgehammer to the problem.
A sledgehammer or a bulldozer, yeah.
Yeah.
And this isn't just a minor software debate for developers either.
No, not at all.
The path we choose between RA and long context, it dictates the entire future of how human knowledge is going to be stored, retrieved, and processed by machine intelligence. It dictates the infrastructure companies will have to build, the compute costs they're going to have to pay, and fundamentally how much we can actually trust the answers we get.
Okay, so let's unpack this. We have to cure the amnesia.
Yes.
Let's start with the first major architecture, which the industry has spent, the last few years obsessively building?
Pretty much, yeah.
RAG, Retrieval Augmented Generation. Let's break that down.
So it's an elegant concept that relies on an incredibly complex underlying mechanism. The philosophy of RAG is actually really simple. Don't teach the AI everything. Just give it an incredibly efficient research assistant.
Okay, I like that analogy.
Right. So when you ask a question, the assistant runs to the archives, finds the 3 relevant paragraphs, hands them to the AI and says, here, read this, then answer the user.
That sounds perfectly logical, but the blueprint for building that assistant is where things get really wild.
Oh, absolutely.
Let's trace the actual data pipeline here. Say your company has a massive library of documentation. Thousands of PDFs, legal contracts, dense technical manuals.
A typical enterprise setup.
Right. You can't just throw that at the AI. The very first step in a RAG system is actually a destructive one.
Yes, it is.
You have to take all your beautiful, cohesive documents and run them through a chunking algorithm.
You literally slice the documents into fragmented pieces. You might set your chunk size to, say, 500 characters or maybe a few paragraphs. You basically systematically dismantle your entire library.
Okay, wait. I have to push back on this right away.
Go for it.
Because if I take a meticulously written 50-page legal contract where, Clause B completely depends on the context of Clause A,
Right.
and I just run a digital meat cleaver through it, chopping it into 50-word chunks, aren't I inherently destroying the meaning? How is breaking the context the first step to providing context?
You've identified the original sin of our egg right there.
Really?
Yes. Chunking is an inherently lossy process. You lose things.
Yeah.
To mitigate what you just described, engineers employ strategies like sliding windows.
Sliding windows.
Yeah, where chunk 2 contains the last 20% of chunk 1. It creates this overlap so sentences aren't just cleanly severed in half.
Oh, I see.
Or they use recursive chunking, trying to mathematically respect natural paragraph breaks. But your fundamental point absolutely stands. You are shattering the holistic structure of the document because the downstream system physically cannot swallow the whole thing.
Okay, so we have a mountain of fragmented text chunks. Just a pile of digital confetti.
Confetti is a great word for it.
But the AI still can't read that efficiently, right? So we introduced the translation layer, the embedding model.
Yes.
And this is where the source gets really interesting because we're moving from language into pure mathematics. We take every single one of those text chunks and pass them through this embedding model.
And the embedding model's entire job is to translate human semantic meaning into a spatial location.
A location.
Yeah, it turns the text into a vector.
Okay, let's really explain this because the word vector gets thrown around a lot in tech right now. We aren't just talking about a simple code, right? Like A equals 1 and B equals 2.
Oh, not at all. A vector, in this context, is a high-dimensional array of numbers.
Okay.
Imagine a geographical map. You have latitude and longitude, 2 dimensions that let you pinpoint any city on Earth.
Sure.
An embedding model does exactly that. But instead of mapping physical space in 2 dimensions, it maps semantic meaning in, say, 1,536 dimensions.
Wait, what? My brain hurts just trying to picture a 3-dimensional graph, let alone 1,536 dimensions.
Right. You physically can't visualize it, but the math is beautifully consistent. In this multidimensional space, concepts that are related to each other are plotted physically closer together.
Give me an example.
So the mathematical coordinates for the word dog will be physically close to the coordinates for a puppy or canine.
Oh, okay.
And it captures complex relationships too. The classic example in data science is that if you take the vector coordinates for king, subtract the vector for man, and then add the vector for woman, the resulting coordinates land almost exactly on the vector for queen.
That is wild. It's literally quantifying the vibe of the language.
Exactly. Quantifying the vibe.
It's turning the abstract concept of like a company vacation policy into a massive unique string of coordinates.
Yes.
And once we've done that to all our chunks of corporate data, we need a warehouse to hold all this math. Enter the vector database.
A specialized database designed specifically to store, organize, and rapidly search millions or billions of these high-dimensional number arrays.
Okay.
So at this point, your preparation is complete, your documents are shattered, they're mapped into a 1,536-dimensional universe, and they're locked in a database.
Which brings us to the actual moment of truth.
The user prompt.
Right. The user types a question into the chat box. How many vacation days do I get after 5 years? How did the array system actually know which piece of confetti to grab?
This is where the magic of semantic search happens. The system takes the user's question, how many vacation days do I get after 5 years, and runs it through that exact same embedding model.
Ah, so it transits the question too.
Exactly. The question itself is translated into a vector, plotted as a specific point in that same 1,536-dimensional space.
So the question becomes a coordinate, and then the vector database basically just looks around its immediate neighborhood.
That's a perfect way to put it. It measures the mathematical distance between the user's question and all the chunks of data stored inside it.
So it's not just doing a keyword search for vacation.
No, not at all. It's looking for chunks of text that share the same conceptual geometry. It calculates what we call the cosine similarity, the angle between the vectors.
Okay, the math is doing the heavy lifting here.
Right. The chunks with the smallest angle, the ones mathematically closest to the question, are deemed the most relevant. The database retrieves those specific, highly targeted chunks of text.
And here's the final step, right? The augmented generation part of RAGA. We take the user's prompt, we take the 3 paragraphs of the company manual that the vector database just spat out, and we bundle them together.
We invisibly inject all of that into the LLM's context window.
Right. We basically tell the AI, here is the user's question, and here is some highly relevant background information we just found for you.
Yeah.
Now formulate an answer.
And the amnesia is temporarily cured. The model reads the retrieved context and generates a perfectly accurate, beautifully formatted response about the 5-year vacation policy.
I mean, it's an absolute marvel of engineering pipeline design.
It really is.
But as the IBM technology breakdown makes painfully clear, There is a massive structural vulnerability hiding in plain sight here.
Oh, a huge one.
This entire elegant ballet of chunking, embedding, vector math, and cosine similarity,
Yeah.
it all balances on the razor's edge of hope.
And hope is a terrifying foundation for enterprise architecture.
Totally. It relies entirely on the hope that your semantic search actually found the right snippet. If the math slightly miscalculates, or if the user's phrasing was weird and plotted the vector in the wrong neighborhood, the database pulls the wrong chunks.
And if you hand the LLM the wrong study materials, it doesn't matter how much of a genius it is.
Right.
It's going to confidently give you the wrong answer. The bottleneck of intelligence in a RAG system isn't the large language model. The LLM is just a formatting engine at the end of the pipeline.
Wow, just a formatting engine.
Essentially, yeah. The actual bottleneck is the retrieval step. If your retrieval algorithm fails, the entire system fails. You've built this fragile, complex chain of dependencies.
So if RAG is this incredibly delicate, highly engineered tightrope walk that constantly risks dropping the ball, what happens when we just get fed up with the finesse?
We bring in the bulldozer.
Right. What happens when we decide to smash right through the wall? This leads us to the second massive architectural shift we need to talk about today, long context.
If RAG is a scalpel, long context is definitely a bulldozer.
A bulldozer that just clears away the entire pipeline we just talked about. The source literally describes this as the brute force method, the model native solution.
Yes.
You look at the vector database, the embedding models, the chunking algorithms, and you just throw all of it in the trash.
You bypass the pipeline entirely.
You take your raw documents
Right.
in their entirety, and you just shove them straight into the context window of the LLM.
You skip the research assistant entirely.
Yes.
You just walk into the genius's office and dump the entire filing cabinet on their desk.
Which is so funny to picture, but for a long time we couldn't do this, right? The source grounds us in a bit of vital history here.
Right. Context is important.
The brute force method wasn't an option a couple of years ago because the models physically couldn't handle it. The underlying architecture of these models, specifically the transformer architecture, has a very strict limitation on how much short-term memory it has.
The context window.
Right, the context window.
And early large language models had context windows that were, by today's standards, just claustrophobic. We are talking about limits of maybe 4,000 tokens.
And let's clarify tokens quickly for everyone. A token isn't exactly a word, right?
No, it's more like a syllable or a piece of a word.
Okay, so 4,000 tokens is maybe 3,000 words?
Roughly, yes. It's a few pages of text.
That is nothing. You couldn't even fit a short corporate white paper into a 4K context window, let alone a massive knowledge base.
And this is exactly why RAG was born. RAG wasn't just some fun engineering experiment. It was an absolute architectural necessity.
Because the window was so small.
The context window was so tiny that you physically had to have a system to aggressively filter down the universe of information into just the 3 most vital paragraphs.
Right.
Because if you tried to paste a 50-page document into a 4K window, the model would just crash. It couldn't process the sequence.
But here's where it gets really interesting. In the last year or so, the technological landscape has completely shattered those limits. Today's frontier models are not constrained by 4K windows. The source highlights that we are now looking at models boasting context windows of 1 million tokens.
Some are even pushing 2 million or more.
1 million tokens. The scale of that leap from 4,000 to over 1 million, it really requires a moment of pause.
The engineering breakthroughs required to achieve that are staggering. Primarily in optimizing how the model calculates attention across such a massive sequence without just instantly running out of GPU memory.
To make 1 million tokens visceral for us, because human brains are pretty bad at big numbers, the source gives us this fantastic benchmark.
I love this analogy.
It's so good.
Yeah.
1 million tokens is roughly 700,000 words. That means you could take the entire text of the Lord of the Rings saga,
The whole thing.
the Fellowship of the Ring, the Two Towers, the Return of the King. You can take all of Tolkien's sprawling epic, hit copy, paste it into a single prompt box, and you would still have enough blank space left over to paste in the entirety of The Hobbit.
It completely alters the paradigm of human-computer interaction.
It's mind-blowing. You aren't searching for chunks anymore. You are taking your company's entire 500-page onboarding manual, your entire codebase repository, and just dropping the whole raw file straight into the chat.
And fundamentally, this shifts the burden of work.
How so?
Well, with RAG, the burden of finding the answer is placed on external mathematical databases, right?
Right.
With long context, you are forcing the LLM's own internal neural network, specifically its attention mechanism, to do all the heavy lifting.
So the model does the search itself.
Yes, the model reads the entire mass of text simultaneously. Its attention mechanism assigns mathematical weights to every single word in that million-token sequence, figuring out exactly which sentence on page 400 relates to the question you asked.
Wow.
It does the searching, the synthesizing, and the reasoning all at once inside its own brain.
And with this monumental leap in capacity, it forces a very uncomfortable question for the industry.
A very expensive question, too.
Yeah. If we can just hit Command V and paste the entire library into the prompt, do we actually need vector databases anymore? Have we spent years perfecting this intricate RAG pipeline only to watch it become completely obsolete overnight?
Does the raw horsepower of the bulldozer render the precision of the scalpel irrelevant? That is the central debate in AI architecture right now.
The IBM technology source lays out a very compelling case for essentially killing RAG.
They do.
They present 3 core arguments for why stuffing the context window directly might be the definitive way forward. And the first argument is something that every IT director listening is going to resonate with: collapsing the infrastructure.
Oh, absolutely. The source brilliantly refers to this as moving to the no-stack stack.
The no-stack stack. Let's talk about the sheer weight of maintaining a RAG system in production. It is a heavy, precarious beast.
It's a lot of moving parts.
Think about what a development team has to manage. First, that chunking strategy we talked about. You have to constantly tune it. Are your chunks too big, too small? Are you losing context? Then you have to pay for and run the embedding model API.
And you have to provision, secure, and monitor a dedicated vector database. That's an entirely separate piece of infrastructure that your database administrators have to learn and manage.
But wait, it doesn't stop there. Because semantic search isn't perfect, most advanced RAG systems require a re-ranker.
Ah, the re-rank.
Yeah, a secondary AI model that looks at the 20 chunks the database found and reevaluates them to pick the top 5 before finally sending them to the LLM.
And we haven't even touched on data synchronization yet.
Oh man, synchronization.
This is the real nightmare. If your HR department updates a single sentence in the company policy document on a Tuesday, your system has to instantly detect that change, delete the old vectors, re-chunk the new document, re-embed it, and update the vector database.
Wow.
If that sync pipeline stalls for even an hour, your AI is confidently giving your employees outdated information.
It is a massive, brittle pipeline with a dozen different joints where things can break, stall, or fall out of sync. Now contrast that nightmare with the elegant simplicity of long context. It genuinely is the no-stack stack.
The architecture simplifies down to its most primitive form. There is no vector database.
None.
There are no embedding APIs. There are no re-rankers or chunking algorithms to tune. The pipeline is just retrieve the raw file from your normal storage and send it to the LLM. Done.
The appeal of that, just from a maintenance and engineering cost perspective, is astronomical.
Huge.
But the second argument for killing RAG gets deeper into the actual quality of the AI's output. It targets the fundamental flaw we touched on earlier, the retrieval lottery.
This is where we examine the mathematical risks of probabilistic matching.
Right. Our RAG relies on semantic search. It's trying to find the closest mathematical distance between your questions vector and the documents vector. But the source emphasizes a critical point here. Semantic search is an educated mathematical guess.
It's a guess.
It is not a deterministic database query like in SQL search.
No, it is entirely probabilistic. And because it relies on the geometry of language, it can be easily fooled.
How so?
Well, if a user phrases a query using terminology that the embedding model didn't heavily associate with the terminology used in the document, the vectors just won't align.
Oh, I see.
The math will fail to see the connection, even if a human would instantly recognize it.
And this introduces the most terrifying phrase in enterprise: AI silent failure.
Explain the mechanics of silent failure for us, because it's crucial to understand why developers fear it so much.
Think about it like this. The exact answer you need is sitting perfectly written in a PDF somewhere in your company's archive. You ask the RJ-powered AI the question.
Okay.
The system translates your question into a vector, searches the database, but because of some weird quirk in the high-dimensional math, it pulls 5 chunks that are totally irrelevant. It completely misses the golden paragraph.
So the LLM receives the prompt and those 5 useless chunks.
Exactly. And the LLM has no idea that the system failed. It just assumes those 5 chunks are all the information that exists in the world on this topic. So it confidently generates a completely wrong answer, or it politely tells you that the information doesn't exist in the company files.
And it fails silently.
Silently. You don't get an error code flashing red on your screen saying retrieval failed.
Yeah.
You just get a smooth, articulate, completely incorrect hallucination.
You've essentially created a system that is blindly confident in its own ignorance.
But with long context, you completely eradicate the retrieval lottery. There is no lottery to play.
You own the casino.
Yeah, you don't have to hope the system pulls the winning chunk because you just handed the AI the entire casino. The LLM gets to see every single word of the document natively. It doesn't rely on a secondary system's mathematical guess.
It removes the middleman, and with it, the highest probability of silent failure.
Which naturally leads us to the third argument for killing Arigo. And honestly, this is the most fascinating one to me because it exposes a limitation in Argy that no amount of engineering tweaking can really fix.
The whole book problem.
The source calls it the whole book problem. Yes.
This is where we transition from simple fact retrieval to complex multi-document reasoning. And it is where the fundamental architecture of RAG just hits a brick wall.
So what does this mean in practice? Let's say the answer you're looking for isn't a specific stated fact. What if the answer is actually a gap in the information?
Right.
RAG is brilliantly designed to retrieve what is explicitly there. It matches a vector to an existing vector. But how does a mathematical equation retrieve an absence of information?
It can't. Let's explore the specific example provided in the source material because it perfectly illustrates this failure mode.
Let's do it.
Imagine you're a software developer and you have two distinct documents. Document A is a 50-page product requirements. Document everything the software was legally contracted to do.
Okay.
Document B is a 50-page release notes document. They're the summary of what the software actually does now that it's launched.
Okay. 2 big documents. Now, you asked the AI a highly analytical question. Which security requirements were omitted from the final release?
Now, let's trace exactly how the RAG pipeline processes that query.
Okay, you type in your query. The embedding model turns omitted security requirements into a vector. The vector database looks for chunks that mathematically align with concepts like security and requirements.
And it does exactly what it's programmed to do. It successfully finds and retrieves 5 chunks from the product requirements document that detail the planned security features.
Right.
And it retrieves 5 chunks from the release notes that mention the implemented security features. It hands these 10 isolated snippets to the LLM.
It grabs the isolated chunks, but here is the fatal flaw. It cannot retrieve the gap.
No.
Because RAG only shows the model a handful of disconnected snapshots, the LLM never gets to see the full, holistic picture of either document.
Exactly.
It cannot cross-reference the entirety of document A against the entirety of document B. It is impossible for the LLM to realize that, say, requirement number 47 on page 12 of the requirements doc is missing from the release notes.
Because it never saw page 12.
Right, because the vector database never retrieved page 12 because page 12 didn't look like a direct mathematical match to the user's prompt.
What is like trying to determine what piece of a 1,000-piece jigsaw puzzle is missing by only being allowed to look at 10 randomly selected pieces.
That's a great way to put it.
You cannot deduce the negative space without seeing the entire assembled picture. RAG is fundamentally blind to the negative space.
To answer that question, the model physically needs both of those entire documents in its memory simultaneously.
That has to have them.
It needs to perform a sweeping line-by-line comparison. And that is exactly what the long context bulldozer does. It solves the whole book problem by quite literally dumping both whole books into the prompt.
The AI's internal attention mechanism reads both 50-page documents completely, maps the relationships between every requirement and every release note, and explicitly deduces exactly what was left out.
Long context allows for global reasoning over the entirety of a data set, whereas a RAG restricts the model to localized reasoning over fragmented snippets.
It's an incredibly persuasive argument.
It really is. When you look at the evidence, the massive fragile infrastructure overhead of the ARG pipeline, the constant danger of silent failure in the retrieval lottery, and the utter inability of ARG to handle complex gap analysis like the whole book problem, you really have to pause.
Yeah.
I mean, is ARG actually dead? Is the vector database just a transitional technology? Are we going to look back at it the way we look at dial-up modems, a necessary hack before we got real broadband?
It is a very seductive conclusion, especially when you see a model process The Lord of the Rings in seconds.
I know, it's so tempting.
However, The architecture of information processing is rarely determined by a single variable like capacity.
The Empire Strikes Back.
Yes.
The IBM technology source pauses the execution of ARG and steps in to argue why the vector database is, in fact, far from dead. They present three massive counterarguments that prove why ARG is going to survive the era of the million-token context window.
While long context clearly wins on the metric of architectural simplicity, REG still holds vital, fiercely defended ground when it comes to economic efficiency, accuracy at extreme scale, and the fundamental reality of enterprise data limits.
Let's break down these counterarguments because they expose the hidden costs of brute force. And the first one hits directly at the wallet. The source calls it the rereading tax.
We have to talk about the physical economics of compute power. Simplicity is rarely free, and the bulldozer approach burns an astronomical amount of fuel.
Right. There is a massive hidden catch to dumping a 500-page manual into a prompt. Long context creates a massive compute inefficiency. Let's use a tangible example here.
Okay.
You have a technical manual for a piece of industrial machinery. It's 500 pages long. The source notes that 500 pages equates to roughly 250,000 tokens.
Now imagine you deploy a long context architecture. You build a chatbot for your mechanics, and every time they ask a question, the system places that entire 250,000 token manual into the context window.
A mechanic asks a simple question. How do I reset the primary pressure valve? The LLM ingests the entire 250,000 token manual, processes it, finds the answer on page 412, and spits it out. Amazing.
But then, 5 minutes later, a different mechanic asks a second question.
What is the recommended hydraulic oil type?
Here is the brutal inefficiency of long context. The model has to process that entire 250,000 token manual every single time a user hits enter.
Every single time.
It has no persistent memory of the document between queries. It has to reread the entire 500-page book from scratch, calculating the attention weights for every single word, just to answer a one-sentence question about oil.
It's an unbelievable waste of computational power. You are paying the API cost, the server time, the literal electricity required to read a book over and over and over again, thousands of times a day.
Yes.
You are paying a massive rereading tax on every single interaction.
Now compare the economics of that to the efficiency of RAG.
RAG also has to process that 500-page manual, but it only pays that heavy computational processing cost once.
Just once.
It pays it at indexing time when it chops the manual up, runs it through the embedding model, and stores the math in the vector database. Once those vectors are locked in the database, the heavy lifting is permanently finished.
So when the mechanic asks about the hydraulic oil, the RAG system's semantic search mathematically finds the single chunk about oil in milliseconds.
Milliseconds.
It hands the LLM a 100-token paragraph. The LLM only has to read 100 tokens to generate the answer, not 250,000.
It is the difference between opening a massive textbook, going to the index, finding the page number, and turning directly to it, versus forcing yourself to reread the textbook, starting from the title page, every single time you need to look up a definition.
The compute savings of RAG at scale are just immense.
Now, to be rigorous, the source does introduce a technological nuance here that attempts to save long context. There is an emerging optimization called prompt caching.
Prompt caching.
So if the document doesn't change, the system can kind of save its state, like it remembers that it already processed the manual.
Exactly. Without getting too deep into the weeds of KV caches, the system basically saves the mathematical state of the processed document. If the exact same document is passed in the next prompt, it skips the heavy reading phase and pulls from the cache.
Okay.
For highly static data, like a completed novel or a fixed technical manual, prompt caching can significantly offset the rereading tax.
But the source immediately points out the fatal limitation of caching. What about dynamic data streams? Think about your live corporate environment.
It's never static.
Your company's Slack channels, the active code base where developers are committing new code every hour, live customer service ticket logs. That data is constantly mutating.
But if the document changes by even a single comma, the cache is invalidated.
A single comma.
A single character change means the system has to process the entire massive file from scratch. For dynamic data, prompt caching is pretty much useless.
Wow.
You are stuck paying the full processing tax of hundreds of thousands of words on every single request. RAG bypasses this entirely by only updating the specific vector chunks that changed.
So, efficiency is a massive point for RB. But the second counter-argument from the source is even more surprising.
This one is my favorite.
It addresses a fundamental flaw in the cognitive ability of long context. It challenges the entire premise that bigger is better. The source calls it the needle in the haystack problem.
This one is fascinating because it directly contradicts our basic human intuition about how these models work.
Right. There's this intuitive assumption that if I hit copy on a document and I paste it physically into the context window, the AI now knows it. The data is right there. It has to see it.
That is the logical assumption. But empirical research into the architecture of large language models reveals a very different reality.
As these context windows have exploded from 4K to 100K and now pushing a million tokens, researchers are observing a degraded reasoning phenomenon. The models are suffering from diluted attention.
Wait, I'm stuck on something here. If the attention mechanism in long context is so powerful that it can process a million tokens, why does it suddenly get diluted? Shouldn't a bigger, more advanced brain just be able to hold more information perfectly?
That's a great question. It comes down to how the transformer architecture distributes its focus. The attention mechanism uses a mathematical function called softmax.
Okay.
It basically assigns a probability weight of importance to every word in the sequence. But as the sequence grows massive, as you push toward a million tokens, that mathematical attention gets stretched thin, it gets diluted.
Let's visualize the nightmare scenario. You drop a 2,000-page financial report into the prompt,
Oh boy.
and you ask a highly specific question about a single solitary footnote that happens to be buried dead in the middle of page 1,000. It is the ultimate needle in a massive haystack.
Because the model's attention weights are spread across millions of words, and because it inherently tends to pay more attention to the very beginning and the very end of a prompt.
The lost in the middle phenomenon.
Right, a well-documented quirk. It often just glazes over that footnote. It fails to retrieve the needle.
The signal is completely drowned out by the noise of the haystack.
I mean, it gets worse than just failing to find it. The LLM feels fundamentally compelled to answer your prompt. It's designed to generate text.
It wants to please you.
Yeah. If it loses focus on the actual answer because it's overwhelmed by the 2,000 pages of context, it will often hallucinate.
It will confidently stitch together an answer pulled from surrounding irrelevant paragraphs or just revert to its base training data.
It becomes disoriented by the overwhelming volume of context you've provided. You force-fed it too much information, and its actual reasoning capabilities degraded as a result.
And this is exactly where the finesse of RAG absolutely shines. The primary advantage of RAG is that it completely removes the haystack.
By relying on the vector database to perform that semantic search first, RAG filters out the noise before the LLM ever sees it.
Exactly. It doesn't drop 2,000 pages on the AI's desk. It retrieves only the top 5 most mathematically relevant chunks.
By retrieving only the top 5 chunks, RAG presents the model with just a handful of needles.
It forces the model to focus purely on the signal. The LLM's attention mechanism isn't diluted across a million tokens. It is hyper-focused on 500 words that we already know contain the exact match to the user's query.
And that fixes the hallucination problem.
It drastically reduces hallucinations because there is simply less irrelevant text for the model to get distracted by.
It is a profound realization. Sometimes restricting the AI's context actually leads to much sharper, more accurate reasoning.
Less is more.
Okay, so RA saves us a fortune in exactly a context window of a million tokens, 700,000 words. Sounds unbelievably huge when you are a single person trying to summarize a book. But in the grand scheme of an enterprise organization,
A million tokens is nothing.
it's a rounding error. It's a drop in the bucket.
When you look at an enterprise data lake, the totality of a major corporation's knowledge, we are talking about decades of corporate emails, terabytes of codebase history, thousands of sprawling internal wikis, financial records, every legal contract ever signed, every customer service transcript ever recorded.
We are not measuring that in millions of tokens. We aren't even measuring it in gigabytes. We are measuring enterprise data in terabytes and often petabytes.
A million tokens is a tiny fraction of a single gigabyte. An enterprise data lake is orders of magnitude larger.
You simply cannot hit Command A on a petabyte of corporate data and paste it into a prompt window.
You'd break the computer.
It breaks the fundamental laws of physics and computing. You would run out of GPU memory before you processed 1% of it. And here's the hard truth. The context window, no matter how much the Frontier Labs expand it in the next 5 years, will never, ever be large enough to hold an infinite data set.
The data will always outpace the active memory.
Always.
And because of that undeniable fact of scale, if you want an AI to have access to an infinite data set that stores everything your company has ever produced, You absolutely must have a retrieval layer.
You need a system that can sit on top of petabytes of information, sift through it in milliseconds, and filter it down to a tiny, concentrated cup of water that the LLM can actually fit into its context window without crashing.
You need a warehouse to hold the infinite and a librarian to fetch the finite.
And that means the vector database, the embedding models, and the entire RAG architecture remain the only viable solution for true enterprise-scale AI. RAG is not an unnecessary complexity layer. It is the permanent fundamental bridge between infinite storage and finite processing power.
So we've taken this massive technical journey through these two competing architectures. We have two incredibly powerful approaches, and they each have distinctly different strengths and glaring weaknesses.
Long context gives us beautiful, no-stack simplicity and the magical ability to reason across whole books and spot missing information.
But it costs a fortune in compute, struggles with dynamic data, and risks confusing the AI with diluted attention.
On the other hand, RAG gives us incredible compute efficiency, hyper-focused accuracy, and infinite scalability.
But it requires a massive, fragile tech stack to maintain, and forces us to constantly play the probabilistic retrieval lottery.
So how does an IT director or a developer or just a curious user actually choose their weapon?
If we connect this all to the bigger picture, the decision isn't a holy war about which technology is inherently superior.
It's not bar rag versus long context forever.
No, it is entirely about matching the architecture to the specific constraints of the problem you are trying to solve. We can establish a very clear matrix for decision-making based on the source's findings.
Let's lay down that final synthesis. How do they know when to use which?
The primary dividing line in the matrix is the boundary of your data and the complexity of the reasoning required. If your specific problem involves a bounded dataset, meaning the universe of information you need to analyze is contained within a discrete, manageable size.
Like analyzing a specific 100-page legal contract, summarizing a single research paper, or trying to find the omissions between two specific product requirement documents. Basically, if the data actually fits comfortably inside the context window without hitting the upper limits.
Yes. And crucially, if the task requires complex global reasoning, meaning the model needs to hold page 1 and page 100 in its head simultaneously to deduce a gap or a relationship, then long context is unequivocally the winner.
It vastly simplifies your tech stack. You don't need to build a massive, complex vector database just to analyze one contract.
No.
You just drop the contract in, let the attention mechanism do its work, and leverage that global reasoning.
Exactly. The simplicity and the reasoning advantages far outweigh the compute inefficiencies when you are dealing with bounded, discrete tasks. However, the matrix shifts entirely when you move past bounded data.
Right. If you are trying to build an internal AI assistant, a corporate co-pilot that needs to navigate the infinite data set of your entire enterprise knowledge base.
The terabytes of scattered wikis, the decades of history, the petabytes of logs.
If your data is effectively boundless, the decision is made for you by the laws of computing. The vector database and the RAG architecture remain the only viable warehouse.
You must have that retrieval layer to filter the infinite ocean down to a manageable drop, forcing the AI to focus only on the needles and ignoring the haystack.
It really is a fascinating architectural divide. We started this deep dive talking about LLMs being frozen in time, these brilliant minds trapped in an isolation chamber.
Yeah, the amnesiac genius.
We watched engineers build intricate RAG bridges, literally chopping up our words, turning them into high-dimensional math coordinates, and building specialized vector databases just to inject a little bit of our reality into the machine.
And then we witnessed the bulldozer approach. The brute force magic of simply expanding the LLM's memory, finding out we can fit Tolkien's entire bibliography into a single prompt, letting the model read it all instantly to spot the gaps.
And finally, we arrived at the sobering realization of scale, that no matter how big the model's memory gets, the sheer crushing scale of human data will always outpace it, dictating that we will always need a librarian to manage the archives.
Always.
So we turn it back to you. Think about the data you are trying to manage in your own projects or your own company. Are you team long context, leaning into the no-stack simplicity for your bounded tasks?
Or are you team RAG, building the intricate mathematical library to tame your infinite data?
Or perhaps, as is often the case in brilliant engineering, are you finding a way to build a hybrid, routing simple queries to the vector database and complex gap analysis to the long context window?
This raises an important question, actually.
Yeah.
A final thought to mull over as we look beyond the immediate engineering choices of today.
Lay it on us.
We have spent this entire deep dive intensely debating the mechanics of how to feed information to the machine. But consider the inherent flaws embedded deep within both systems.
Okay.
Semantic search, the heart of AG, currently relies on a retrieval lottery that risks silent failure because mapping the geometry of words doesn't always equal understanding contextual intent.
Right.
And long context suffers from diluted attention, hallucinating because the AI physically loses focus when drowned in a sea of words.
Both systems, at their absolute limits, ultimately struggle to perfectly grasp human intent when they get overwhelmed.
Exactly. So we're ultimately chasing a mathematical mirage. Perhaps the future isn't about choosing between the perfectly tuned RAG pipeline and the infinitely large long context window.
Then what is it?
Perhaps the real horizon is questioning if human language, with all its unspoken nuance, its messy ambiguity, and its vast unstated context, can ever be perfectly translated into the pure, rigid mathematics required by either of these architectures.
Will the machine ever truly understand the meaning behind our words, or will it forever be trapped, just trying to calculate the distance between them? Something to think about the next time you drop a document into a chat box.